So if you have been given this line right here, one of the things you can do is put it in slope-intercept. So we would then move the x over, so that would become a negative x minus 3, and then we would divide everything by that negative 3. So we have y equals 1/3 x plus 1. So you would start at 1 and go from there. So if I start at 1, positive 1, a 1/3 slope is going to take me up 1 and over 1, 2, 3. And then I'm going to connect those lines, those dots there. Now, what I will say is when you're doing this process that we're about to do, you want to be very precise in when you graph these. All right, and I'll show you how to be as precise as possible. All right, the second graph that they gave us, or the second linear equation that they gave us, was x plus y equals 5. This one's rather simple, just move that guy over. Negative x plus 5. So we're going to start at positive 5. Negative 1 over 1 takes me here. If I were to walk that all the way down, each time, down 1 over 1, down 1 over 1, you can see that this guy right here is also going to be a point on that line. All right, and so if I connect those, and you can see they cross each other at the point 3, 2. And so right here is where those two lines cross. All right. And so that's what we're actually going to be doing today. We are going to be solving what's called systems of equations using our graphing skills that we did in the last chapter. So if you look at page 278, it explains it at the top. It says in this chapter, you'll be working with more than one equation at a time. So in the last chapter, we did just one linear equation at a time. We put it in slope-intercept. We used point slope. We found the slope. We graphed them. But now we're going to be doing systems of equations. So we're going to be doing more than one linear equation at a time. So it's made up of two or more linear equations. Any ordered pair that makes all of the equations true is a solution to the system. All right, so normally if you have a true statement, that means you can plug in your values and it gives you the answer that makes sense. All right, it gives you a true statement. And so the first thing we're going to look at is, what does that mean? So example 1 says, determine whether each ordered pair is a solution to the system. All right, so they want to know if the ordered pair is a solution to the entire system, which means in order for it to be a solution to the whole system, it has to work for this equation and this equation, both of them. All right, and so how do we check that? Well, we are going to check it simply by plugging it in. So we're going to take the point 11, 2, and we're going to plug it into each one of these. The first one is x minus y. X is 11, y is 2. And then we're going to plug it into 2x plus y. 2 times 11 plus 2 equals 9. And we're going to see if those are true. Well, for the first one, 11 minus 2 is 9. Yes, that is true. For this one, 2 times 11 is 22, plus 2 is 24. 24 does not equal 9. So this one is false, which means the coordinates that they gave us, 11, 2, is not a solution. It worked for one, but not the other. In order to be a solution to the system of equations, it must work for both. It must work for both, and it does not. So this one is not a solution. When I plug it into both, it does not work. Let's look at the next one. We're going to look at the coordinates 6, negative 3. We're going to do the same thing. X minus y. 6 minus negative 3. X minus y equals 9. And then 2 times my x, which is now 6, plus negative 3 equals 9. All right, we're going to check these. For the first one, 6 minus a negative 3. Remember, minus a negative is the same thing as plus a positive. So 6 plus 3 is 9. Yes, that is true. For the second one, 2 times 6 is 12. 12 plus negative 3 is 9. Yes, that is also true, which means that 6 negative 3 is a solution. So that is a solution to this system of equations. System of equations. It must work for both. All right? It must work for both. So for these examples that we just did, they handed you the coordinates and they said, is this a solution? All right. What we're going to be actually doing in this chapter is we are going to be finding those solutions. All right. And the first way you can actually find a solution is to graph it. So here's the thing. Every graph that you do for a line represents every single coordinate that works for that line's equation. All right. So when we did x plus y equals 5 and we graphed that line, you could have picked any point on that line and plugged it into x plus y equals 5, and you would get a true statement, all right? Every single point on that line will work for that linear equation because that line represents every answer that works for the line, all right? So then when we graphed two lines, right, we had every answer that worked for x plus y equals 5. We had every answer that works for x minus 3y equals negative 3. All right? Which means that where they crossed over works for both of them. Does that make sense? So if I have every answer for one line and every answer for the other line, and they intersect, then that means that where they intersect is the point that works for both of them. Now here's the deal. If they are two distinct lines, meaning they're not the same line, there's only going to be one answer that works for both of them. Why? Because lines only intersect once, all right, in everything except spherical geometry. That's another story. We'll talk about it next year, okay? But in Euclidean geometry, in what we define as a line right here, they intersect one time. And so it's not like they're going to intersect and come back around and intersect again. That's not going to happen. And so if you graph the lines and you see where they cross, then you are finding the one set of coordinates that works for both of those equations, meaning you're finding the answer to the set of linear equations. And so this is the first way we're going to solve. Here are the steps. Graph both equations on the same coordinate plane, all right? Identify the solution, which means you need to figure out what that point is, the xy value of that coordinate. And then you can check it by plugging it back in. Now, here's the thing with graphing. Graphing, you have what's called human error if you're not using some type of device to graph, okay? And so you want to be as precise as possible. So very often I'll pick my 2 points, but then I will walk up my graph. So I won't just do 2 points. I'll walk, if it's 1/2, I'll go up 1 over 2, up 1 over 2, so that I can see precisely where it's going to hit that other line, okay? And that way you're a little more accurate, because this is really the least accurate way to do this, because you have human error of, you know, my ruler was tilted wrong, or I didn't use a ruler, or whatever, and so you can do just sketching errors when you're sketching the graph to the line. So you want to be as precise as possible when you are graphing these. All right, let's look at this first example. Solve the system by graphing. So we are going to graph exactly the way we've done. I recommend graphing in slope-intercept form because then you have your slope and you can walk it. If you graph it using your x and y intercepts, it may not be as accurate because you're not walking with a slope unless you find your slope and you walk from there. All right, these are already in slope-intercept form, so we're going to go that way. All right, so we're going to look at y equals negative x minus 2. So we're going to start at negative 2. That's my y-intercept. My slope is negative 1, which means I go down 1 over 1, or I can go up 1, left 1. So down, right, up, left. And then, of course, I am going to connect those dots. All right, connect those dots. So I'm going to graph that line. Then I'm going to graph my second line. All right, my second line is y equals x minus 4. Y equals x minus 4. So I am going to, for this line, I'm going to start at negative 4. My slope here is positive 1, so up 1 over 1, and you can see just by the first thing that I did where they're going to cross, all right? If you don't see it on your first move, you may want to keep moving until you cross that line so you can see exactly where they cross, all right? But you can see where they cross here, so I'm going to go ahead and graph this line, all right? That's my first step. Then I'm going to say, where do they cross? Well, they cross right here. What is my coordinate for that point? My coordinate is, my x value is 1, my y value is negative 3. So 1, negative 3. And so if I were to answer this question based on this graph, my answer here would be 1, negative 3. That is my answer. Your answer for these should always be an xy. Always be an xy. There is a way to check it. You're going to check it just like we did our first example. You can plug it back in if you want to check these. And so you can say, well, y equals negative x minus 2. So y equals negative x minus 2. Negative 3 equals negative 3. That is true. Y equals x minus 4. So y equals x minus 4. Once again, negative 3 equals negative 3. You can see that my answer holds true. This is the correct answer to this question. So if it says solve by graphing, it wants you to graph both lines. It wants you to figure out where they cross, and that xy coordinate, you should name it your xy coordinate. I need the x and the y values. That is your answer. To check your answer, you plug it back into the two equations you were originally given. Now this particular one is not in slope-intercept form. All right. Again, I prefer graphing them in slope-intercept form simply because you can walk the slopes if you need to. And so the first step here then is to get it in slope-intercept form. So if I start with my x minus y equals negative 5, I need to move my x over. I have negative y equals negative x minus 5. And don't forget you need to divide by that negative 1. So I get y equals x plus 5 for that graph. So I would start at positive 5. I would go up 1 over 1, up 1 right, or down and left. And I would have this line right here. Connect those, you have your first line. All right, the second one, we have 3x plus y equals negative 7. So I want to move my 3x over. I have y equals negative 3x minus 7. Now, I'm going to start down here at negative 7. My slope is negative 3 over 1. That would move me off this graph, and it's really not the best way to walk it if I'm walking towards the other line. So remember, I could also do positive 3, negative 1, which means I'm going to go up 3, 1, 2, 3, and left 1. All right. Now, what I mean by walking this, up 3, left 1, that puts me here, all right? Up another 3, left 1, puts me right here. Up another 3, left 1, puts me right here. Not a pretty dot there, but, all right? So I can see where I'm going to cross the line if I walk it with my slope, all right? If I just were to do those 2 points, let's say I just did these 2 points here and I had not walked it, then human error, I could have moved it in between and you'd be like, oh, it's not directly on one. Do you know what I mean? And so if you walk it all the way to the line you're trying to cross, you will see exactly where they cross. You'll see exactly where they cross. And so it's more precise. Oh, that's not precise. All right, there we go. And so you want to connect those. You want to see where they cross. And then, of course, if you want to check your answer, you can plug it in. So first, what is my answer? Well, my answer is my x value. That's -3. So I have an x value of -3 and a y value of +2. +2, all right? I can check to see if they work. I can plug them in. -3 minus 2 equals -5. Yes, that is true. 3 times -3 plus 2 equals -7. -9 plus 2 equals -7. Yes, that is true. So I can see that my answer, -3, 2, is correct. But there are possible solutions to your systems. The first one is the one that we have been doing, where they just intersect and you have an answer, right? So we have intersecting lines here and they cross, all right? Or you could have parallel lines. Now, if they're parallel lines, they never ever cross, which means there is never a time when they have the same exact solution. So the answer to this system is no solution. You'll notice no solution, or this symbol right here, which looks like an O with a line through it, or even a 0 with a line through it sometimes, means no solution. And so if you were to get parallel lines when you graph, you can write no solution, or you can do the symbol for no solution, but you need to somehow tell me that there is not an answer because there is no point that works for both of them. The last thing is coinciding lines, meaning it is the same exact line. So when you graph them, you get the same exact line, which means there is an infinite number of solutions. This entire line is the answer because every single point on the line works for both lines because they're the same line, pretty much. All right. So look at example 4. Example 4. They are not in slope-intercept form. And so before I even graph it, I'm going to try to put it in slope-intercept form here. So I'm going to look at the top one. All I have to do for that one is to move that x over. So I would get y equals negative x plus 3. For the bottom one, I need to move the 2y, just divide everything by that 2. All right, so divide this by 2, this by 2, and this by 2. And I get y equals negative x plus 3. What do you notice about those two equations? Hopefully you notice they're exactly the same, okay? And so if I were to graph this, I would get the same exact line. Now, if it says solve by graphing, then you're going to graph it, all right? And so if it says solve by graphing, you're actually going to put that on your coordinate plane, and you are going to see that it is the same line, obviously. But your answer here is the entire line. It's the entire line of negative x plus 3. It's this whole line. And so your answer for this would be the entire line. It's not one point, it's the whole line, okay? The whole entire line is your answer there, all right? Make sense? All right, let's look at the other one. Now for the other one, they've given us x plus y equals 3, so we're going to move that over, and we're going to get y equals negative x plus 3. They've given us x plus y equals 7. We're going to get y equals negative x plus 7. Now, if you don't remember this, you're about to see it in the graph, but what do you notice about their slopes? They're exactly the same, but their y-intercepts are different. So hopefully you know these are parallel lines, because in the last chapter, we learned that parallel lines have the same slope. But if it says solve by graphing, you're going to solve by graphing. So you're going to say positive 3, down 1 for my slope, and over 1. And so I get a line that looks something like this, right? And then the second line starts at positive 7 and goes down 1 and over 1. And so I get a line that looks like this. Those are parallel lines. I know it two ways. I know it because I graphed it, and I know it because my slopes are the same. And so for this one, your answer is not going to be one of the lines. Your answer is going to be no solution. And so you would tell me there is no solution to this. One way or the other, you would tell me no solution. And that would be your answer for this particular systems of equations. All right? And so there's multiple ways to get answers, or multiple types of answers you can get. The most common is going to be they intersect at one point. They can be parallel, no solution, or they can be the same line, which means it is an infinite number of solutions. All right? Drew is considering two options for financing a used car. The loan from the bank. The first bank requires $3,000 down and $250 a month. The loan from Bank B has the same interest rate, but requires $2,000 down and $350 a month. All right? Write a function to describe the options, then graph. All right? So if I'm talking about Bank A, all right, then my loan amount is going to, and we'll just say they wrote it as cost. Cost is going to equal an initial amount down of $3,000 and $250 per month. All right, and X plus B. Bank B, the cost is going to be $350 a month. That's my slope. And $2,000 down. That's my y-intercept, all right? So your starting amount, just think about how you graph. How do you graph? You graph starting at your y-intercept. So your starting amount is your y-intercept. The amount per whatever is your slope. 250 per month, 350 per month. When you see that, that is slope because that's how you're moving, okay? So think about starting amount, y-intercept. What's changing every single time, that is your slope when you have these word problems. And you can see when they graphed it, where do they have the same exact amount paid? It's right here. At 10 months, they will have paid out the same amount. So if you're financing for more than 10 months, one's going to cost more, one's going to cost less. You can see how one line starts going higher, one line starts going lower than that, right? And so he's figuring out what's my best way to finance this car. Why do you think I would want you to solve word problems different than graphing? Why would there be, if there's multiple ways to solve, this is the first way, why do you think graphing isn't the way I would choose to solve a word problem? Accurate. So if you see these huge numbers, right, we're starting at 3,000, we're going up 250 and over 1. There's a lot of room for error when you're graphing these huge numbers, right? It's like you're not going to be able to walk 250 up and 1 over, right? You're going to have to be estimating here. And so figuring out, you're basically approximating when it's going to happen, which businesses do approximate because it is, based on what they think is going to happen. But when you're trying to do it a little more precise, then there's some equation solving that we're going to be doing as well. So there are times when graph is really simple, these really simple lines, and you're going to graph them and figure out where they cross. But there are going to be times when they don't cross at a perfect amount. And so then all of a sudden you want to be a little more precise than trying to see where they possibly cross on a graph. And so typically with word problems, I do it one of the other methods so that you can be more precise with your answer versus you're sketching a graph.